Hey, and welcome to Vodcast number 6. We're going to talk about the empirical formula today. Please note that this is the empirical formula, not the imperial formula. It's just one of those things that makes chemists skin crawl if you call it the imperial formula. It's the empirical formula, and we're going to talk about this only briefly. This is going to be one of the shortest of our vodcasts. Because we're just introducing the idea, and we'll talk more about calculating the empirical formula when we get to vodcast number 7. So this is just a quick introduction, and if you have any questions, please make sure and come and see me. This is Miss Carr, and this is Mole Vodcast number 6. Okay. Today we are going to be talking about the empirical formula, and the empirical formula is simply a reduced form of the molecular formula. That means that when we look at a molecular formula, it may not be reduced to its simplest form. So the empirical formula is the simplest form of that molecular formula. In effect, you want to simplify or reduce the same way you would with fractions. And to give you a bit of a review of how to reduce fractions, we're going to take a look at this. But you've been doing this in math since probably early middle school. So I'm not too concerned about your ability to reduce. If you are struggling with how to reduce fractions, you can definitely come and see me, make some time, and come in for tutoring for this. But this is a mathematics skill that you should come into my class with. I just want to make sure that we take some time to review it so that you can make sure that, yes, you know how to do this. So let's take a look at a fraction like 2/4. Of course, 2/4 can be reduced with the 2. Both of these numbers can be divided by 2, and so we can turn this into 1/2, right? So if we look at 3/9, for example, both of these numbers can be divided by 3. So a reduced form of 3/9 would be 1/3. And another example would be 8 and 12. Both of these numbers have a common denominator. We have that common factor of 4. So we can reduce that to 2/3 because 8 divided by 4 is 2 and 12 divided by 4 is 3. And 2/3 cannot be reduced anymore because there's no number that you can divide both 2 and 3 by to make it anything other than 2 or 3. Okay. 1/3 is an example of a already reduced fraction. Of course, we can't reduce it anymore. So a reduced 1/3 is still going to stay 1/3 because there's, again, no number that we can divide 1 and 3 by to get anything but 1/3. Okay. So that's just a quick review of how to reduce fractions. You're looking for something that both the top and the bottom can be divided by. So in your empirical formula, it works the same way. It's simply a reduced form of the molecular formula. So I'm going to give a few examples here with the molecular formula on the left and the empirical formula on the right. Follow along and see if you can figure out how we're going about doing this. It's fairly simple, especially once you get that how to reduce your fractions business. Okay, so your molecular formula of CH4, this of course says that we have 1 carbon and 4 hydrogens. So that's 1 and 4. Well, there's no way to reduce 1 and 4 because it's already reduced to 1. You already only have 1 carbon. So the molecular formula for CH4, which is carbon tetrahydride, or also known as methane, your empirical formula for this substance is the same because the molecular formula is the most reduced form that you have. Okay, so the next molecular formula that we have here is C2H6O4, and this is an organic molecule that you would see in biology related to your carbohydrates, right? So you have C2H6O4. You'll notice that all of these numbers of atoms can be divided by the number 2. So if we divide the number of carbons by 2, we end up with 1 carbon. If we divide hydrogens by 2, we end up with 3. If we divide the number of oxygens, then we end up with 2. And that gives us our empirical formula, which would be CH3O2. If you can review and come back, you see that we simply divided each of these subscripts by the common denominator, which here is 2. right? So we divided the C by 2, we divided the H by 2, and we divided the O by 2. So the simplified or reduced version of the formula is CH3O2. Okay. This next one is glucose. It's a molecule that you should be very familiar with after having taken biology. This is, of course, the product of photosynthesis and the energy unit for cellular respiration. So we have here glucose, which is C6H12O6. And if you notice, this is a formula, a molecular formula that can be reduced because all of these numbers in the subscripts can be divided by 6. So if we divide everything in the problem by 6, we end up with C only 1, H 2, and then O only 1. So you have CH2O is the reduced or empirical formula for glucose. Now, you will never see a glucose molecule that has this formula because the molecular formula is C6H12O6, but this is simply our reduced or empirical formula. We're going to talk about when you would ever use an empirical formula in our next podcast. So this is simply a way of saying that this is the most simple form of this molecule. This is a reduced formula for this molecular formula. Okay, so we have H2O. If you'll notice, this is 2 hydrogens and 1 oxygen. And if, in case you haven't already figured it out, this is another example, like methane, of a formula that has already been reduced. So you can't reduce it any further. This is the same as saying 1/2. You can't reduce 1/2 any further. So there's 2 hydrogens, 1 oxygen, and you can't divide that by anything because the oxygen, there's only one of them to begin with. So the next one up is the molecular formula for N2O4. You'll notice that both the 2 and the 4 can be divided by 2, and that leaves you with the empirical formula of NO2. All right. Our last example is C4H12O8. Of course, all of these can be divided by 4, leaving us with the empirical formula of CH3O2. Now, you may have noticed something if you were paying attention when we did the earlier empirical formula, where up here you have CH3O2 and down here you have CH3O2. So you have 2 molecules that have the same empirical formula, but have 2 very different molecular formulas. This one is a 2-carbon carbohydrate, and this one is a 4-carbon carbohydrate. This is going to come into play when we start talking about the molecular masses of these 2 substances, because the molecular mass of these 2 substances is going to be very different. But when you look at the empirical formula remains the same. So this becomes important when you're talking about things like percent composition, because when you calculate percent composition, the composition of this substance is going to be the same as the composition of this substance because their empirical formulas are the same. Okay, and that's it for the empirical formula introduction. When you're done here, you can begin your worksheet, worksheet part 6, where you can calculate the empirical formulas for the substances listed there. If you need any additional help, make sure to come and see me during class time and check in for your next progress report. All right, I'll see you guys in class.